think I owe you the definition of a matrix in reducible echelon form. So let me write it down. By the way, if my handwriting is not so clear, you please let me know. Okay? I will correct it. Okay, so here we call as promised in reduced law echelon form, all the leading non-zero entries of each non-zero row will be scaled to 1, right? Scaled to 1, right? And those 1 here will be called pivot. Okay, so this one is a pivot, this one is a pivot, this one is a pivot. Okay, so each non-zero row is 1 as its leading non-zero entry. Okay. Oh. Yeah. Okay, and in each column containing a pivot, then there is no other non-zero entries, so all has been eliminated, right? By replacement, so we can eliminate them by replacement. Okay, and well, so I think I have to write this one as 1, 0. Okay, I think I have to write because that even for augmented matrix that we have to if this the last row is a non-zero, then you have to scale it leading non-zero to 1. Okay, so you have to put that. I can't put a cross because when I put the cross here means that it can be any value. Okay, and but for reduced law echelon form, that if it is non-zero, it must be 1. So this is a pivot. But we will not call it as a pivot. So that is an exceptional case. Okay, so I have to give you a forcing. If we are talking about okay, so I have to amend something. Each such leading one in the coefficient matrix. Okay. It's called a pivot. So they are pivot. But this one is not a pivot. For some historical reason. So this dash line is very important. To give to you to know that if we are considering an augmented matrix, because the last column corresponding to the right-hand vector, right? And so the coefficient, and here is just the coefficient vector. So let me say here is the coefficient. And the whole thing is augmented. And so the third point is true because that in each column containing a pivot, Okay, so these three are figures, and there are no other non-zero entries. But for this non-zero entry here, the column corresponding to this one may have non-zero value. Because we will not do elimination for the right-hand vector. It's very important because once you do that, okay. And of course, that if this situation happened, it has a very serious consequence. I will tell you later. Because it says that the corresponding system linear equations has no solution. Okay, so it's very serious. So if the corresponding system linear equation has at least one solution, then this entry must be zero. Okay, but I'll talk about that later. So the amendment is very important here because we call this one they are figures, but this is not. Okay. And the figure in any row follow to the right, then the figure goes above. Okay, that's all. Okay. So that's why because the right-hand column is very spatial. So that's why initially I just put a cross here, but I would like to bind to the one here. Okay. Any questions? Remark. So the location here is just the first column and first row and second column. So this location is called a pivot precision. Okay. All right. So we have three pivots, and so we have three pivot precisions. Another terminology which will be referred to later on. Questions? So if no further questions, so let's move to the second. So that we already used matrix notations to represent the system linear equations. So this section we will examine this technique further. Okay. So consider a rectangular matrix. when I mention matrices, I mean rectangular matrices. Okay? Right, so we consider two rectangular matrices. So they may have different dimensions, but the number of columns, which is n of A, is equal to the number of rows B. Okay, so you can see that. So sometimes we write the dimension of the rectangular matrix here in just the corner at the left-hand side. Right, so it means that this rectangular matrix has dimension m times n, and B has n times k. So n is the number of rows of the matrix, and n is the number of columns of the matrix. Similarly, n is the number of rows of matrix B, and k is the number of columns of matrix. Alright? Then the product C of A and B is defined as so CIL with CIL equal to summation Aij and BJL J for 1 for all and from 1 to M and that index I'm sorry from 1 to K. So when we look at here, okay, I1, So basically we take the I-scale. So this is matrix A, this is matrix B, and here is the first column. Okay, so take the I0, which has n components, and we take the else column, which also has n components, and multiply the entries, corresponding entries one by one, and add them together. Okay, so this is just like for the index here. So AI1 times BI1 plus. So this is actually AI1 B1L plus AI2 and B2L plus the central AIN BNL. Okay. So to get the product of two rectangular matrices, you have to deal with the right dimensions for A and B such that the number of columns of A should be equal to the number of rows. Otherwise, the product cannot be defined. Okay. So you know this factor from high school. Okay, so this is A and B, and give to you L. Let's row, let's column. Okay, so that so you have these entries. Let's see. Okay. Is that okay? Remark. Row vectors and column vectors are spatial kind of matrices, which has dimension So row vectors are matrices of dimension 1 times n, because it has only one row, right? And column vectors, column vectors and column vectors with dimension m plus n times 1 matrices. One. Second, a linear system of linear equation of n linear equation with n unknowns. Right? And so the A here corresponding to 8.1. Okay, so let's see the corresponding dimension. The coefficient matrix A is also, of course, a matrix. So the dimension is m times n. So m represents the number of rows corresponding to a number of linear equations in the system, and the columns of A actually corresponding to this number n is just the number of unknowns, and the unknown vector x is a column vector, so it's n times 1 matrix. Okay, so now you can see that n is equal to this n, right? So this product is meaningful according to our definition of the multiplication of two matrices. And so the n is what? The ending is m times 1. So the dimension of B, the right-hand vector is an m times 1 matrix. So of course it's a column matrix. So it's fit to our definition. Questions? Now, we let A, J, be the fifth column of A. Right? Then A can be written as one, two, H is a row of column vectors. Okay, so we can think about that. So this is the whole thing. The first column can be A1, so it's a vector. The second column, 2, and the last column. Okay, so we have n columns here. And so we arrange the columns one by one in this order. So actually, the matrix A can be represented as a row of column vectors. Okay, now, in this way, okay, the product. Okay. Will be written as to x1, so you can check, okay? You can check them. Right, so please show it by yourself. We just write down because so actually this is equal to just to be your hint. This is comes to summation and of course you cover back to the system linear equations, the left-hand side. Okay, the left-hand side here. Right. And so in any case, actually, for any matrix with this notation. So this is the common practice that we regard. So if a multiplication of two matrices like this one is a matrix, but this one is a column matrix or column vectors, then you can expand. Or I use expanded. Alright, I use it for Okay, so now I want to mention a couple of properties. One, so let's see. Okay, and the dimension. So A and B has the same dimension. C and D has the same dimension, but it's different from A and B. Okay, so A and B are this way. Oh, I'm sorry. I'm sorry. No. I want, because associated law, n times a times L. Sorry. But so they have different dimensions in general. Then A times B. So we can get the product of A and B and multiply with C. The result is equal to, you can do it. You take the product of B and C first, and then multiply with A, but in the same order. Okay. So that you know that the dimension of this product is M times K, and this is K times L. So of course, no problem with that. But what is this? The dimension of B and C is n times L, and A is n times n. Okay. So together the dimension is m times L. Together the dimension is m times L. So by checking the dimensions, you see that it is consistent with this identity. It is very easy to check. If you want to know whether an identity is true or not, you can first check the dimension. If the dimension is not consistent with each other, then of course it's false. Okay, so that is the necessary condition. Okay. Alright, so this is called the associative law, that when you multiply a sequence of matrices with right dimensions, then you can do it in any order. Okay, so for this example, if we multiply three matrices together, so you want to get the product of A and B and C, then you can do it AB first, and then the result multiply with C, or you can do BC first, and then A multiply with the result BC, and they can do the same. Okay, it's called associative law, and it is to be proved. But it's a little bit tedious, so I think I don't want to do it in this classroom right now. But please check it by yourself. Okay. So let me finish the other law before we take a break. Okay, so it's called the associative law. The second property is called the distribution law. Alright, so this time let A, B, and D, and the dimension here is A and B has the same dimension, n times n. C and D has the same dimension, n times n. Then, and A times C plus D. Alright? The reason why C and D should have the same dimension because that we want to do the addition of two matrices, because only same matrices can be added together. Otherwise, if two matrices have different dimensions, then they cannot add together. Okay. Right, and so this law is that you can take the product of A and C, and take the product of A and B, and add them together. Similarly, if we have this way, then it's AC plus BC. Okay, so they are you can check the dimension first. Okay. So place. So we can check these two properties. Matrix multiplication. i.e. it is possible that A and B are going to be for example, if this is n times n and n times k, right? Okay, so fine, this product is meaningful. But if you exchange the order, do the multiplication, then this is n times k and n times k. Then if k is not equal to m, then b and a is undefined. Okay, so even in this situation, it's undefined. Now, necessary. Right? A necessary condition for commuting the product will be true. It's that m equal to n equal to k. Why? Well, by dimension, because that if this is true, so if we want the proof, okay, let me give you a proof. Yeah. If AB equal to BA, right? Suppose this is true. This is true. Now, and we know that this is m times n, this is n times k in general, right? But in this case, we must have because from here now we have n times n. Okay. And so this is n times k and m times n. Then, okay, then we are forced that m equal to k. Okay? otherwise GA is undefined. So M equal to K. But the result, if M equal to K, so the result, and then, from right here, AB equal to PA becomes M times, and this is M times M. Okay. But now the matrix here is M times M, so it comes to a square matrix of dimension M, and the result is N times M. Right? And from here, because we have identity, so M must be equal to N. Okay. So we have a conclusion. So if commutativity is true, means that if this is true, then to check dimension, we must have M equal to N equal to K. Alright. So A and B are square matrices, okay, with the same dimension. Now, but even for square matrices and B, okay, so even for square matrix and B of dimension we may have A times B not equal to B times A. So the necessary condition is not sufficient. Okay? So even though we have square matrices of the same dimension, the commutativity property, if you commute the order, then commute the product, then that's the result is bigger. Okay, so you know that this condition is just a necessary condition of such an identity, but this condition is not sufficient. So this gives you an idea. Necessary condition, sufficient condition. Okay, so this is a lot. Okay, alright, so now we will consider square matrices. Okay, so from here we will consider only square matrices of dimension n times n. The identity is square matrix I very special that it has all 1 through the diagonal entries, but other entries are all zeros. Okay? So this is a very special kind of square matrix of dimension n times n. It's called the identity matrix. And the notation is I n times n. Sometimes I will write in, okay? Sometimes. All right. Now consider a square matrix X A if there exists another square matrix C is the dimension, okay? Such that A times C equals to C times A equals to the identity matrix. So if this fact is true, it means that we can find a square matrix C such that A times C is equal to the identity matrix, as well as C times A is equal to the identity matrix. Then A is called invertible. Okay? Right. So at that time, when I mentioned a square matrix is invertible, if we can find the square matrix C such that this is true. Okay, so you have to make sure this is true. 3 minutes. Any question about the definition? Or property? Uniqueness of I use lemma if the square matrix A is invertible, such that A is CA and So the question is that if we find one, say if A is invertible, means that we find a square matrix C such that it's identity. And the next question is that if we find one, can we find another one? Alright? Means that if we find a C, can we find another D which is different from C, right? And so the lemma says that if this is the situation, then C equals D means that no others. If there exists a matrix C satisfying these identities, then such a C is unique. Okay, and so the proof. What is it? Okay. Okay. All right. I can finish it. CI. Oh, by the way, I forgot to mention a property of identity. Property. A times I equal to I times A equal to A. Okay. So if I have identity matrix, then so this is M times M. They are all M times M matrices. Right? No. Okay. So CI. Now C, but I is equal to AB here, right? Now by the associative law, CA, so I can multiply CA first by the associative law. But this is I, because here equal to I, and D, so this is D, and finish. Okay? Next time. Okay, so I have used this property. This is trivial, right? Any square matrix comes with the identity matrix will be the set. So no problem. And so I use this back, and then I substitute because of the identity AD here. Okay, and then by associative law, I can multiply this first. Try this one again, ID finish. Okay, so let's go for the quiz number 1.